Okay. They have not protested. Anyway, today we'll have the third lecture about offshore technology. The problem is I have so much I would like to share with you and tell you about. I'm not sure I will be finished today, or we have to use a little bit of time on Monday. We'll see. Okay, so we have already seen quite a few pictures of various types of offshore systems, and I think this one is a one that shows maybe greater variety of the type of installations that can be at an oil field, as a matter of fact, at the same time. So there can be platforms of different types, right? We have talked about platforms. There can be a FPSO. And here you see also it's called umbilicals. It's also called a flexible riser. And the reason why it's like this is that the ship will move, right? So it has to be flexible. Here you can have stiff risers, and also this is a TLP, I believe. And then you see some well heads, and they are collected. They come together in a manifold where they are combined. So there are manifolds here, and there are control systems. So this is a special technology that we will not go too deeply into, but of course this is an area where there's a lot of development at the moment. And of course you also, as you put more and more processing on the seafloor, you need energy for this. So you'll have, typically now you have electrical cables that go to the subsea systems and provide power for not only the various valves and control systems, but also as a part of the processing system. You may do various types of processing even at the seafloor. Yes.
How do we install the kind of facilities the
How it's you have to, of course, as much as possible is finished onshore, right? Taken out with these, let's say, ships with big cranes or special crafts for heavy lifts, and lowered down to the seafloor. And then you have to do all the connectors. You have to connect the pipelines and the power cables and all sorts of things down there. And when you are more than, let's say, 250 meters, you cannot use divers. So you have to have subsea robots, either autonomous or remotely operated, right? So this is certainly an area where ROVs and AUVs are being used, and completely necessary for the technology, right? Because you cannot have people down there. Of course, you can have people inside some underwater vehicles, but certainly not divers. There have been experiments with divers down to more than 400 meters, but it's a tremendous health hazard. And many divers have been damaged for life in this kind of operations. So nowadays, one is doing all of this automatically with remote control. Yes?
What is satellite based?
The satellite?
Satellite based.
Well, this is where the wells are coming up, and you see these are not connected to a manifold, but they are going directly to the platform, right? But I'm not a specialist. This is where the oil well is, right? Or oil and gas. And then it goes into a pipeline. Typically, you'll have something where you have two fluids or even three fluids at the same time in the pipeline, because here you have not processed, right? If you have processing, then of course you can do some separation, let's say sending the oil in one pipeline and the gas in another. But nowadays one has technology for two-phase flow, that is just both a gas and a fluid, oil mixed with water in the same pipeline. So that's advanced technology. Guideline-less, I guess that is, I must admit I'm guessing, but I guess what is meant here is that these are connectors to wells where you don't have any power supply. And here you have some power supply, right? So there are some, this pipeline technology is, or deep water pipeline technology is also continuously being improved. And I remember many years ago, when we did some nonlinear finite element analysis of pipelines, and then the so-called trench outside the Norwegian coast that went down to, let's say, 350 meters for some of the oil fields on the outside, that was considered the limit for being able to lay a subsea pipeline, the limit depth. But nowadays, the limit is more than 1,000 meters. So technology is improving all the time. So there have been some, recently over the last, let's say, 8 to 10 years, some very big projects. You can see a pipeline for gas going from Russia to Turkey. If you Google Blue Stream pipeline, you'll get a lot of data about that project. And there's one that has just been finished from Norway to England. So the gas is first taken to shore, and that is the Ormen Lange project. I'll talk a little bit about that. And then it's shipped all the way, you see, to Great Britain. But I think here in the middle there's a so-called booster, and the booster is then increasing the pressure in the pipeline, because you have friction, of course. Even if it's a gas, there is friction and lowering of pressure. So you need to boost up the pressure to have sufficient speed of the gas going through the pipeline. This is a project that is going on right now from St. Petersburg to Germany, all the way through the Baltic Sea here. I don't remember how long that is, but it is order of some 1,000 kilometers. So these are enormously long pipelines. And I saw an announcement earlier this month, and this is something that has been discussed for some years, but now the decision has been made to build a pipeline from Oman to India. You see, 2,000 kilometers pipeline. And in this case, I'm not sure they are able to have any boosters, or they may have to have some subsea boosters for increasing the pressure. And it goes down, I think it goes down towards 1,000 meters. So this will be an enormously challenging project to pipe the gas from this region to India. And India, of course, is now booming. You know, the gross national product is increasing very, very rapidly, and India needs a lot of energy. And of course, gas is, after all, a better alternative than oil and coal. So there's quite a bit of news about this project recently. So how is this done? And here you see a pipe-laying ship. And here is more heavy equipment. It's more like a semi-submersible, right? And you see what's going into the sea here is called I think it's called a stringer. So what is done is you have this pipe-laying vessel, and you know it's some sort of barge, and here you have this support structure that looks like this. Then you produce the pipe on board. You weld together these sections of pipe, and the pipes are often covered with bitumen and, you know, this tar stuff and concrete, and you have automatic welding of these sections, and of course you have to grab the whole thing to hold it, and then the pipeline is fed into the sea, right, like this. And of course you have to have either very strong propulsion, because you need a pulling force, otherwise the whole thing would go back and it buckles. So you have to have a strong pulling force, or you have to have a tugboat, right, that pulls this thing. These are not very good. I'm afraid our friends at the other campus will not see very much of this. Understand the principle? So here you can see typically pipelines stored, and when you need 2,000 kilometers, how many pipes? This is interesting too. When you are closer to land, for instance in an area where there is fishing, you may have to dig and hide the pipeline in the soils on the seafloor. So you may have to excavate on the seafloor, and then you put the pipe in the trench. And sometimes you have to put stones on top of that. Other times you just wait for, let's say, the current to fill the trench. But this is subsea excavator. See that? So it's lower to the seafloor, where it, you know, goes like this and digs this trench. So it's quite remarkable what can be done. This is high strength steel, but of course it has to be weldable steel, right? Well, it's pretty stiff, but of course, when you have such tremendous lengths, it bends, you know. But if you lose the pressure, the pulling force here, it will buckle. It will buckle, and there's even something called a propagating buckle. If you get a buckle here, it may start running because of the water pressure. As soon as you get a initiation of buckling, it can run almost with the speed of sound along the seafloor, and the pipe ends up looking like this because of the water pressure. That's called dog boning. Looks like a dog bone.
So how could it change?
Change? Normally you don't want to change the pipeline.
So I think in the under the sea, the common steel might be cooling.
Yes, but you know, if you have a damage or you want to connect a new pipeline, you know, you may have to cut it. You may have to lift up the parts that have been cut and put in a new. I'm not sure how that is done, but they can replace a damaged pipeline. But also you need to have a monitoring, a checking of the condition of the pipeline all the time. And then there's something called a pig. Have you heard about this? A pig, it's not a pig like that, but it is a mechanical device that you send through the pipeline with the gas flow. And it can measure the thickness of the steel as it goes along on the inside and comes up on the other end. Yes?
Why not put a pipe in vertical position? That pipeline is horizontal.
Yes?
Why not put it in vertical?
Well, you see, first of all, each section, I'm not sure if it's 20 meters or something like that. In principle, you could, you know, put it together in a long tower, right? But I'm sure that has been considered. So what they do, you know, you have to bend it regardless when it comes down. It's in one way, it's not better to come down to the sea floor like this, is it? So this is a better profile than that profile when it comes to the amount of bending that you subject the pipeline to. You see, you need this horizontal component. You need this force component in order for this bending not to be too much. You have to pull it in order not to have it too much curved here. So this is probably the biggest and most advanced subsea development so far, and it's at Ormen Lange. This is outside the coast of Norway. Here you have the city of Trondheim, where you have NTNU, the Technical University, right there. And what they have done is to develop a field at up to 1,200 meters water depth. So we're talking about, of course, pipelines down at this water depth. And this is primarily a very large gas field. And this gas is then taken from subsea into this land processing plant. And then it's sent from this processing plant all the way over to England. And that was what I showed you, this Langeled project going from Norway all the way to England. And laying a pipeline, and you see, of course, this is in one way exaggerated, but you know, this is the seafloor is not very even. And one of the main concerns is that if you have a terrain that goes like this, and you want to lay a pipeline here, right? You see, you'll have free spans. Free spans. And what is the concern, you think, with free spans? Well, of course, you have some bending there, but that's not the main concern. The main concern is when you have current, and let's say you have a long free span of more than 100 meters, and then you can have vortex shedding, you know, the fluid structure interaction, and the pipeline starts vibrating. And then you can have fatigue in the pipeline because of that. So that is one, you know, computationally challenging problem with this kind of situation to find out whether it's safe or not. In this Ormen Lange project, there are two main pipelines going to shore, and they are 30-inch pipelines. So how much is 30 inches? It's about 70. Yeah, it's 75 centimeters diameter. Yeah. Two of them. And then, of course, there are also cables with electricity and remote control systems and so on. So there are many connections between the subsea field and land. So you see the gas goes to land, processed, sent to England. Two 30-inch pipelines. Now we'll talk a little bit about fluid structure interaction, and I'm sure you have been taught a little bit about it in possibly Professor Park's class. I'm not sure, maybe a little bit about waves in some of the other classes, I'm not sure. So the platform itself, its risers and anchoring systems interact in a coupled and very complex dynamic response. So not only do you have a platform that is moving in the waves, you have an anchoring system, you know, either catenary or a TLP type, and you have the risers, you know, the conductors. All of this interacts. And of course, the great concern is some sort of resonance. Of course, you can do resonance analysis by dynamic formulations, but there are also some higher order response phenomena that are very complex, and I will not get into it in this course, but it's called springing and ringing. And that is, you have, let's say, a response of the platform that goes like this, and then suddenly it goes like this for a while, and then it goes more normal. And you cannot explain it out from normal linear theory. So that is certainly some of the things that have to be considered in situations like this. I've listed some books for you, if you want to have some reference books. So you can click on these and also get price and everything from Amazon.com. This first book is by Professor Faltins, and he is a professor in Trondheim. Sea Loads on Ships and Offshore Structures. So that's the classic, and this one is also a classic, Marine Hydrodynamics by Professor Newman at MIT. So I know both these people. I'm afraid this one is hard to see. And I also have an animation of this to show the complexity of dynamics. Because here you see from a kind of a fish view from below a semi-sub platform. There are anchoring lines going out here that are hard to see, and then there's a set of flexible risers. And in this dynamics simulation, you see the platform moving up and down and rolling, and you see the anchoring line also being stretched and pulled, and you see these risers also go up and down. So today with nonlinear finite element formulations, you can do this kind of simulation, but of course quite complex, and depending also on how much, let's say, fluid dynamics CFD you put into this. Of course, you can do simplifications, but ideally one would like to simulate a serious C state, right, which can be described statistically, and one can have from the statistic distribution of waves, one can have load transfer functions onto the platform and do a time simulation on that basis, or one can do a frequency response analysis. But if the system is very nonlinear, then you have to do a time simulation. And of course, when the platform is moving, you may have to have something called a heave compensator or motion compensator. If you are going to have a pipeline or a conductor from the seafloor and the platform goes up and down, you have to have a more or less constant pull in the pipeline. Then you have a mechanism with a hydraulic system that can pull this up and down in response to keep a constant tension. So again, this technology is not straightforward. And not only do you have to worry about the overall response of a platform or a FPSO, you may also have to worry about what are the local pressures on the body. And as opposed to a ship that, goes and towards the storm, but some of the time is far out in the ocean, sometimes in sheltered waters or at port. A FPSO is lying out there all the time in a very bad weather situation, and one problem is fatigue of not only the ship beam, because that's more a low frequency loading, but the wave pressures that against the sides of the ship also represents a fatigue problem. And why don't you want to have fatigue problems with the FPSO? Well, it's much worse than for a ship, because a ship you take into inspection typically every 5th year. If the ship is not too old, you take it into dry dock. Right? These FPSOs have to operate maybe 30 years without being taken to a dry dock. So if you have to do the repairs, you do it out at sea. And of course, extremely expensive and difficult. So you don't want to take a platform out of operation because it may cost millions of dollars per day. So it's a much more serious condition than for a normal merchant ship. And in these hydrodynamic laboratories, one can also do simulations of this high frequency response that is called ringing and springing. Very difficult, but they are able nowadays to reproduce this kind of response. Then there's something called Morrison's equation. Some of you have heard about that, right? And I'm not sure how much time I should spend on this, but at least I put together some slides for you so you can read about it. But Morrison's equation is used very, very much in offshore analysis. In reality, it is only valid for, or approximately valid for rather small cross sections. But it is used in situations that maybe goes beyond what it should be used for. But as you see on this figure, if you have, let's say, a pipeline or a vertical spar type structure, and you have a wave condition, and in the original version of Morrison equation, one was looking at the fixed body and then a flow that goes back and forth in relation to the fixed body. That's how they do the test in a special lab where they have a water column, or two water columns swinging back and forth, and this kind of flow, of course, gives pressure forces on this body, and you can measure the resulting force. And in Morrison equation, these hydrodynamic forces are divided into two parts. One is the inertia part that has to do with accelerations, and one is a drag part that has to do more with the viscous shear flow. So in Morrison's equation, and U is the velocity of the fluid, and U dot, time derivative of the velocity, is of course acceleration. So you have the density, you have a coefficient, mass related coefficient, you have the volume of the body, and you have this acceleration. That is the inertia term, and then you have a drag term, which is 1/2, and here you can see the kinetic energy. But again, there's a coefficient here that is depending on the geometry of the body. And then you have the area. If you have a flow in that direction, then the area is the outline of the body. But this coefficient depends on whether this is let's say, a sphere, or it's a plate, or whatever. You have different drag coefficients. And here you see the velocity times velocity, what do you call it? The absolute value of the velocity. So this term changes direction depending on which direction the flow goes. You may have to use a little bit more time to understand this, but it is a drag term that is proportional to velocity square, and it is always pointing in the direction of the fluid motion. And this is a version of the same thing if you have a cylinder. This is V and 8 is A is for an arbitrary body. This is what you get per unit length if you have a cylinder. But it is in oscillatory flow, that is flow that goes back and forth. So that was the traditional way of finding the fluid forces on the body, right? But we are very often interested in the opposite thing. We have a structure or a pipe that is moving in the water. You see the difference? This is fluid acting on a body. The opposite is a body moving within a fluid. But of course, in relative terms, it's this relative motion that is counting and making these hydrodynamic forces. So there is a version of this where you have a combination of a moving body in oscillatory flow. So there is an additional velocity v here, which is the velocity of the body. And if you set u equal to 0, you have still water, right? Because u is the water flow velocity. So if that is 0, you see the terms for a body moving in the water. And there too you have one mass term, and you have one term that is associated with accelerations, and one term which is associated with viscosity and velocity square. The Froude number? Yeah, there's a Froude force. This term is called the Froude force. You see that? And then there's a hydrodynamic mass. But this term, you see, only is associated with the motion of the fluid. So that term you cross out if u equals 0. Right? So if you have a situation where your vertical cylinder is moving and the fluid is standing still, then that term disappears. So there is one, the red line, inertia, that is typically a sinusoidal type of motion if you have a sinusoidal type of vibration. But then you have a drag term, which is the blue line, which is a function of velocity squared, right? So a sine function, looks like this, but a sine square function looks like this. And of course, so this is the drag time term, but then it always, the sine comes in, so it looks also like this on the other side. And that's what you see here for the blue line, right? I'm not sure that shape is quite correct. It doesn't look fully like a harmonic square to me. But anyway, it's approximately. And if you add the two, you see this sum is... but what is often done is you have to simplify the drag term, because you do a finite element analysis, right? So linear finite, and here in this case, u is the displacement. So the stiffness matrix times the discrete nodal displacement vector, and then you have the damping matrix, velocities, mass accelerations, right? And if you want to do this, you see that you have to linearize Morrison's equation, because Morrison's equation has u dot the velocity square. And there are various ways of doing that. But if you do a full nonlinear simulation, you can in principle integrate Morrison's equations directly. Whereas in linear analysis, you have to do some tricks. You can find articles about linearizing Morrison's equation. Oops. I certainly am not going to get through all of this today. But I think it's important that we now try to make a coupling between these problems that we see in offshore. And, this is not only oil and gas. This is what you also have to consider if you have, let's say, a wave energy absorbing system, right? Or you have a floating windmill, or you have a fixed windmill. All of these things come into it. As soon as you build something in the ocean, this kind of dynamics that I've tried to give you a little bit of overview of, that comes into play. So I'm trying to couple real problems with what you're learning in your more theory-related courses. And sometimes when you have a more theoretical course, it's hard to understand the motivation, or why do we have to learn this. And at least I've tried to put up some equations and explain how things really are needed in a more practical situation.